Yes. Let me open it. Okay. There are some people waiting in the lobby. Just a minute, let me bypass the lobby for. Yeah, I think that's fine. Okay, so let me quickly go to the method. Let me go to the method of. Yeah, fine. Yes. No. Yes. So let me quickly tell you about the in McCluskey steps. So as you know, there are two steps. Step one is to identify the prime implicants. And step two find out the minimal set of prime implicants. Okay, so all you know is that, so I represent a prime implicant like this. So suppose I have a function which is a summation, the min terms are as follow. Let's say 1, 3, 5, and 7. So this will, so I have 4 variables. So f, a, b, c, and d. So this would mean, so if I write a, b, c, d, the min term should be as follows. What is 1? 1 is a bar, b bar, c bar, d, plus 3 would be a bar, b bar, c, d, and so on. Okay, so similarly 5. So what I will do is that for every min term, I'll write it in this form, of course. This is the same 1, 3, 5, 7, this. So this is 0, 0, 0, 1. This is 0, 0, 1, 1. All right. So index of a, so I'm talking about the step 1. Let's talk about the step 1 first. Index of a min term is the number of ones in the binary representation of the min term. Of the min term. Okay, so so this will have an index of 1 and this will have an index of 2. So what I do, I make a tabular structure. I make a tabular structure. where I group the minterms. This is, let's say, A, B, C, D. I group the minterms according to their index values. So the zero index which have no zeros, so this will be naturally 0, 0, 0, 0. One index, this can be, so in our example, one index is 0, 0, 0, 1. Similar, the ones with index 2. So if there are m number of minterms, the index can potentially be from 0 to m. They can potentially be from 0 to m. Oh no, if there are 4 variables, it can potentially be from 0 to the power m. Sorry, 0 to m. All right. So what you do is you compare two consecutive such groups. You compare two consecutive such groups. Okay, this and this, and every term here with every term here, you compare. And if they can be combined, in the sense that if we have something of this form, you combine them by dropping the x attribute. Okay, so this and this can be combined. If there was something else, maybe 0, 0, not this, this will come here, 0, 0, 1, 1. Similarly, here, if I have, let's say, 1, 0, 0, 1, 1, 0, 0, 0. Okay, so this and this can be compared because they differ by only one attribute. In one position only they differ. So this and this I can compare. Okay, and what I will do is that I will create another table with this reduced number. So A, B, C, and D, and this combined would be 0, 0, and you are dropping D. 0, 0, 0, you are dropping D. The one you are dropping you represent by a dash. And if I number the minterms, let's say I number the minterms 1. Note that this is the index, whereas this is the minterm number. I just label them 1, 2, 3, 4, and so on. Yeah, unfortunately my network is very bad today, but anyway, I think this is the best I can do. Okay, so what I anyway, let me come back to the. Let me take an example. Okay, so let me take what this example means. So can you hear me? Just anybody say, can you hear me?
Yes, sir.
Okay.
Yes, sir.
Yes, yes. So see, let's look at this. So I have a function f of a, b, c, and d, and these are the minterms in the function 0, 5, 8, 9, 10, 11, 14, and 15. All right. So I form a table like this. What this table means is that I have 4 variables a, b, c, and d. If that corresponding variable is in a complemented form, I write 0. So basically, what I am writing here is just the binary representation of these minterm numbers in the places a, b, c, and d. And I group the minterms according to the number of ones they contain. Okay, so this is the minterm 0, and naturally this is the minterm 8. This is the corresponding to the minterm 8. You see, I have put them in 2 groups because it's the first one's index is 0 because it has no ones. Second one's index is 1 because it has 1. All right, and so these are I have written 0, 1, and 1, 1. This D stands for don't care. Right now, I'm not considering don't care, so don't bother about that. All right. So now you see, as I have said, that there is only one variable A which differs. So I'll consider consecutive indexes. So the minterms with, 0 number of ones with 1 number of ones, 1 number of ones with 2 number of ones, and so on, consecutive groups of different index values. So this and this, and I run a double loop. So every element, every minterm in the first group is compared with every minterm in the second group. All right. So you see that so there is no dash here, no don't care here. So this and this get combined. This and so 0 and 8 gets combined. In the visualization of the binary cube that you have seen, this would mean a cube, or in the Carnot map also this would mean a cube covering 2 minterms. If you look at corners of a cube Bn, the Boolean nth Boolean cube thing, there also this will mean a cube, right? So if I combine these two, I get another minterm where this a variable is not there, it's dropped. So I'll replace it by a dash here, and the other variables I copy 0 0 0 0 0 0 I copy. Okay, so these two gets combined to get 0 0 0 and a dash. Here is a slight. Let us consider more minterms. So this is the group containing index 1. So 8 belongs to that group 1 0 0. Earlier I think only. So I was comparing 0 index group and 1 index group. So 0 was there in the 0 index group and 8 was there in the 1 index group. Now let us compare 1 index group containing 8 and 2 index groups containing 5, 9, and 10. Okay, 5, so 8 and 5, 9, and 10. So there are two ones in each of these binary strings and 0 dashes, 0 don't cares. Okay, now as I've said as before, I'll compare 8 with 5, 8 with 9, 8 with 10. So if I can combine 8 with 9 and I get 1 0 0 dash. Note that the position of the dash should be preserved. Position of the dash should be preserved. Similarly, I can compare 8 and 10, combine 8 and 10 and drop C. So I get 1 0 dash 0. Now look at the next group, that is the 2 index group and the 3 index group. 2 index group I have 5, 9, and 10. 3 index group 11 and 14. So let's see, these are the ones I can combine. I can combine 9 and 11, and I can combine 10 and 11 to get 2 dashes. Oh, sorry, 1 dash still. And these are the 1 0 dash 1 and 1 0 1 dash. These are the cubes that I get. Note that this cube is larger than this cube. These are basically points in the binary cube, but these are, so in the Carnot map, this will correspond to 2 cell cubes. Similarly, 10 and 14 I can combine. Okay, so now let's combine the next two groups, that is 3 ones and 4 ones. Here also you see 11 and 15 you can get. 11 and 15, similarly 14 and 15 you can get. Okay, so now we come to the, so see, I have compared between all the elements between ith group and I plus 1th group where there were 0 dashes, and I got a new set of minterms where there were some dashes, 1 dashes actually. There were 1 dashes because 1 variable got dropped after combining these two. The rule of combination is you can combine 2 if they differ in just 1 position. Now let us look at the next group where I have, similarly I index them, I divide them according to the number of ones they have. So this is 1 1 and 1 dash, 1 1 and 1 dash. This is 2 1 and 1 dash. So basically the ones that I got here, 3 1 1 dash, 2 1 1 dash, and 1 1 1 dash, this I am now reducing further. So this I am reducing further. So this is 1 1 and 1 dash, 8 9 that I have got by combining these 8 and 9. 8 and 9, this is what I have got by combining 8 and 9. I'll do it. Okay, and similarly I have 8 10, and then I'll compare this with 2 1s and 1 dash, which is 9 11 10 11 10 14. I compare them. I see 8 9 10 and 11. It is a 4-sided cube in Carnot map. I can combine them. I get A B as 1 and 0, and C and D are dropped. They are dash. note one thing, that what I do is that in each of these tables that I get, I put some kind of a marker, let's say a tick mark, between on the two rows of this table which were combined with at least one other. So 8, 9 was combined with 9, 11, I put a tick. 8, 9 was also combined with 10, 11. 9, 11 was combined with 8, 9, so I put a tick. 10, 11 was also combined with 8, 9. So any row that got combined with anybody else, at least one other thing, I put a tick. Okay, this way I continue. So what I will do in the end is that I will, so if I go forward with the 2 1s and 1 dash with 3 1s and 1 dash, I'll get this. And then at the next level, what I'll try to do is that again, all the cubes with 2 dashes, I'll try to combine among each other. I'll combine with 1 1 2 dash with 2 1s and 2 dashes. I'll try to combine. Okay, and if they combine, I'll kind of put a tick mark. So, so this I'll repeatedly do until either all of them becomes don't care or nothing can be combined with nothing else. Then I stop. If nothing can be combined with nothing else, I stop there. So, and you remember we put a tick mark. So in the end of this process, all the cubes where I could not put a tick mark, where I was unable to put a tick mark, would constitute my prime implicant set. So for example, one prime, if suppose this was not combined further, so AC would be a prime implicant. Similarly, let's say here, not this, let's say here, this could not be combined. Let's say this could not be combined. Then ACD would be a prime implicant. Similarly, you can this way there can be prime implicants even in the first block. So for example, 0 0 0 0 was not combined with anything else. So A bar, B bar, C bar, D bar would be a prime implicant. So anything which is not combined, which is not ticked in this process, would comprise my prime implicant set. So this way, in fact, it can be proved also that this process will give you the complete set of prime implicants. All the prime implicants that are there will be extracted by this process. So now let's go to the second step. In the second step, we form what is called a prime implicant chart. We form a prime implicant chart. So we make a tabular structure. I hope I'm still connected. Let me just, yeah, luckily I'm still connected. Okay, so what I do is that along the rows, the prime implicants that I had extracted, I list them. So 8, 9, 10 and 11, 10, 11, 14 and 15, 0, 8. So the prime implicants that I have extracted in my first step, I list them. And along the columns, I write down the on min terms. That is the min terms that I had. So you remember in this 0, 5, 8, 9, 10, 11, 14 and 15. So these min terms I list along the columns. And I see that which of this prime implicant covers which min term. So this prime implicant covers 8, 9, 10 and 11. These 4 min terms it covers. I'll put a cross in these 4 min terms. Similarly, this covers 10, 11, 14, 15. I'll put a cross in these 4 min terms and so on. Right. So this chart is called a prime implicant chart. This chart will help me find out the minimal set of prime. So what I'll next do is that I will drop some rows and only keep a subset of the rows. I'll just keep a subset of the rows. I'll drop other rows. And what is the requirement of the rows which are retained? The rows which are retained. So see, this row, for example, covers these 4 prime implicants, 10, 11, 14 and 15. Okay. And 8, 9, 10, 11 covers 8, 9, 10, 11, these rows. So the retained set of prime implicants should cover each and every column. Okay. So let's see. So what is the set of prime implicants which cover each and every column here? So here, in fact, all the prime implicants will be required. All these 4 prime implicants will be required to cover each and every column. So what I mean actually is that after dropping some row, I'm willing to drop some row so that I get the minimal set of prime implicants. After dropping the row, if I replot this prime implicant chart, there should be no column without any cross. Every column should have at least one cross. Every column should have at least one cross. So if I want to do that here, actually you can see that I cannot drop any row. I cannot drop any row. Okay, so that's my goal. And so one thing that you might have already thought of is that there are multiple ways of doing it. Which subset of rows will give me a full cover? There may be multiple such subsets. Okay, and not all of them will be minimum. Maybe if I denote minimum as the minimum number of literals present in all these, all the prime implicants combined, all the prime implicants that I written, then each of these may not be the minimal. So what I have to actually do is I have to kind of find the only the rows whose total number of literals is minimum, and it covers all the columns, covers all the true min terms, covers all the one min terms. In this case, you have to do none. Okay, so now naturally this is a search process. Kind of you try out all possible subsets and see which subsets work, which subset doesn't work. And if your number of min terms are large, this might take a good amount of time. Good. So let's see how we can reduce the number of steps required to do this. Reduce the number of steps required to do this. Okay. One thing you see, you first identify the columns which contain only one cross. Which contain only one cross. Okay, so 0 here contain only one cross. The columns which contain just one cross. 5 contain only one cross, 9 contain only one cross, 14 contain only one cross, and 15 contain only one cross. So these corresponding min terms 0, 5, 9, 14, 15 would be called essential min term. No, sorry, they are just covered by. So let's see what are the prime implicants that cover them. So 0 is covered only by this prime implicant 08. So I will call 08 because see, nobody else covers 0, only 08 covers 0. And I need to cover all the min terms. I need to cover all the min terms. I need to cover every column. So naturally, in the reduced set of rows, 08 should be there. 08 has to be there in the reduced set of rows. Otherwise, I cannot cover the first column. I cannot cover the 0 column. 08 has to be there. So 08 is called a essential prime implicant. It has to be an essential prime implicant. Okay, otherwise you cannot cover the 0 column. So can anybody tell what are the other essential prime implicants? Just tell me what are the other essential prime implicants? What are the other essential prime implicants? Yeah. So can anybody tell me what are the other essential prime implicants?
All the rows are essential in this case.
All the rows are essential in this case. Because if you, so the 08 is the essential implicant for 0, 5 is the essential implicant for 5, for 9, 8, 9, 10, 11, similarly for 14, 15, 10, 11, 14, 15. So all these are essential implicant. The rule is that you cannot drop any essential prime implicant. So they have to be there. They have to be there. Okay. But you see, there is one more reduction you can do, because essential prime implicants anyway you cannot drop, so they are always there. let us see what are the other columns covered by this essential prime implicant. So 10, 11, 14, 15, it covers 14, 15, but it also covers 10 and 11. It also covers 10 and 11. Similarly, 8, 9, 10, 11, it covers 8, 9, it also covers 10, 11. So if I keep, say, let's say 8, 9, 10, 11, I am also covering 10, 11. So I can form a reduced prime implicant chart where I have this, I add one row, but I can drop the 10, 11 column because they are already covered. I need not bother about them anymore. I can drop 10 and 11 columns. Okay. If I am, because 8, 9, 10, 11 is an essential prime implicant, I have to have it. Okay. So let me look at another example where, so this is, I'll talk about a series of reductions in the prime implicant chart, which obviously follows. So the first reduction is, since you anyway have to have the drop the columns and form a reduced chart, covered by the essential prime implicants are deleted. This is the first reduction. There are two more reductions that I can do. Okay, let us quickly take another example, and I'll form the prime implicant chart, and you will see that what are the other reductions I can do. So this is in min terms are 1, 2, 3, 7, 8, 9, 10, 11, 14, 15. So this is the first group, 1, 2, and 8. They contain only 1 ones. This is the second group. So can you tell me which are the elements in the first group, m equal to 1, 1 equal to 1, combined with elements in the second group? Can you name answer? So I try to combine 0, 0, 0, 1. With what to combine? Anything that will combine with 0, 0, 0, 1? Anybody? This is easy. I'm just asking you for the sake of asking you. But which combines with which?
So 1 combines with 3.
3 and 9.
1 combines with 9. 3 and 9. So what is 1 combines with 3? I will get a larger consisting of 0, 0, dash 1. Dash means C has been dropped. C said don't care. Similarly, 1 and 9, I get dash 0, 0, 1. Similarly, you can combine 2 with 3, you get 0, 0, 1 and dash. All of this is 8 and 9. 8 and 9 can be combined. Similarly, 8 and 10 can be combined. Okay. So I get a table of two min terms, which have where all these implicants have 1 ones and 1 dashes. Because I've combined 0 dashes with 0 dashes, I've dropped 1 variable, I got a 1 dash. Okay. Now again the 0 dashes but ones, and compare them with 3 ones. So 3, 9, and 8 have 2 ones, and 7, 11, and 40 have 3 ones. So what with what? Give me a list. By the way, tell me, is anything left out from here that has not been combined? Nothing left. 1 has been combined, 1 is there. 2 has been combined, 2 is there. 8 has been combined, 8 is there. 3 has been combined, 3 is there. 9 has been combined, 9 is there. 10 has been combined, 10 is there. So there will be no prime implicant consisting of 4 terms. There will be no prime implicants consisting of all of these are covered. All of these are combined, tick mark. They are reduced. Okay. So none of them will appear in the prime implicant list. Now let's see if any of these appear in the. There may be more. Oh, sorry, I gave a wrong statement. I said that none of these, but I are maybe 4 implicants because I'm not compared 2 with 3. So here I compare 2 with 3. So just tell me what can be compared with what. Let me complete the. Help me complete the chart with 1 dash and 2 ones. 1. What can be combined? Can be combined with 3 can be combined with, please. 3 is combined with, let's see. So 3 is combined with 7. Similarly, 3 is 11. 9 is combined with 11. 10 is combined with 11. They see the rule of combination is they should differ in only one position. They should differ in only one position, and the position where they differ, I replace them by a dash. 10 and 14 combine. Okay, so I get a new set of cubes where one variable is dropped. Now 3 and 4, 7, 11 and 14 have 3 ones, 15 have 4 ones. So you see only 7 and 15 can be combined to get dash 1, 1, 1. Okay, other two are not combined. Other two are not combined. So 11 and 14 is not combined with anybody. So 11 and 14 will be there. Let's see. Oh yeah, okay. 11 and 15 is combined. 14 and 15 is also combined. Okay, combined. Sorry, I missed that. Yes. So everything is combined again. So now let us look at this set of cubes. The first group is they have 1 dash and 1 1. The second set is they have 1 dash and 2 ones. So the first set I have 1 3 1 9 2 3 2 10 8 9 8 10. Second group I have 3 7 3 11 9 11 10 11 10 14. So now I'll again compare every element of the first group with every element of the second group. You know, the rule of comparison again is they will just differ in one position. They have to differ in one position. Okay, which means that the position of the dash also has to match. Dash cannot be combined. The position of the dash has to match. In the remaining time, only one. So just tell me what combines with what? What combines with what? Give me an example. I give you an example. 1 3 combines with 9 11. You see 1 3 combines with 9 11, and A position that drops. So A becomes a dash, B becomes 0, C is already dash, D is 1. Give me one more. Please tell me one more.
Sir, 1 9 combines with 3 11.
11. Okay, one. See, by the way, you see one more thing is that so 1 3 it's not that if it combines with 9 11 I'll stop there. I will also check if it combines with others also. I'll check 1 3 with 10 11. I'll check 1 3 with 10 14. So you see the advantage of this method, of this McCluskey method, Queen McCluskey method, is that you can write a program in a nested loop to check for this. You can easily write. You can find out all the relatives. You can write a program. Okay. So it's the foundation of all computer-aided design tools. Okay. All right. So well, okay. 1 3 combines with 9 11. 2 3 combines with 10 11. One thing you said is that 8 9 combines with 10 11. 8 9 combines with 10 11. Okay. Now we have smaller brackets, larger cubes. We have 1 3 9 11, which is 0 and 1, dash in other positions, and so on. Now let's combine the cubes with 2 1s and 3 1s and have 2 dashes. This is a second level cube. Okay, so 9 11 7 combines with 7 combines with 7 combines with 11 to get dash dash 1 1. 10 11 14 15. 10 11 combines with 3 7 combines with 11 15. 10 11 combines with 14 15 to get this. The others you see don't combine with anything. Okay, 311 doesn't combine. 311, does it combine anything? No. 311 doesn't combine with anything. Similarly here, 715 wouldn't combine with anything. So 311 would be a prime. 715 would be a prime implicant. 715 would be a prime implicant. Similarly, you is 3, 7, 11, 15 and 10, 11, 14, 15. So this category, 2 ones and 2 dash. I don't have large, I don't have anything else. I don't have smaller things. Okay. So these two wouldn't combine with anything else. So these two would also be prime implicants. So what are the prime implicants we got so far? This seed is a prime implicant. AC is a prime implicant. So 3, 7, 11, 15 is a prime implicant. 10, 11, 14, 15 is a prime implicant. Anything else that we have? Anything else that we had? Here, did we have any prime implicant? So 210 is a prime implicant. 19 is a prime implicant. 810 is a prime implicant. 37 is a prime implicant. 311 is a prime implicant. 1014 is a prime implicant because they were not combined with anybody. Okay, they were not combined with anybody. Okay, so see, by the way, it means that 1014 means that the min term 10 plus the min terms 14, which will get reduced to A, C, D bar. B variable will be dropped. So if the cube of size 2, one variable will be dropped. If the cube of size 4, two variables will be dropped. Okay, so using these prime implicants that we have, so let me again recollect the prime implicants: 3, 7, 11, 15, 10, 11, 14, 15, 10, 14, 7, 15, 14, 15, and then here I have 1, 9, 8, 9, 2, 10, 8, 10, 3, 7, 3, 11, 10, 14. So all these are my prime implicants. So using this, so they are all, are they not complete? Yeah, I think. What are we missing? 7, 11, 15 is there. 3, 7, 11, 15, 10, 11, 14, 15, 10, 11, 14, 15. Are there more that can be formed? Are there more that can be formed? Let me check. Maybe I'm making a mistake. I'll just tell you. Okay. 3, 7, 11, 15 is there. 10, 11, 14, 15, 8, 9, 10, 11. What about 8, 9, 11? 8, 9, 11, 8, 9, 10, 11. Yeah, 8, 9, 10, 11 is there. Similarly, 1, 3, 9, 11, 2, 3, 10, 11. These are there. Yes. So this is my prime implicant chart. My prime chart. The essential prime implicants here. I need columns which contain only one cross, and I need to I need to I need to preserve the prime implicants which are covering them. Okay, so what are the essential, and I'll call them as essential prime implicants. What are the essential prime implicants here? Yes, please. What is the essential prime implicant? So 1, 3, 9 is an essential implicant. It covers 1, 2, 3, 10, 11 essential prime implicant. And if 2, 3, 10, 11 is an essential prime implicant, I can drop 3, 10, and 11. These columns I can drop. 11, 15 is a prime essential prime implicant. I can drop as well the column number 3, 11, and 15. Similarly, 8, 9, 10, 11 is an essential prime implicant. 10, 11, 14, 15 is also an essential implicant. Everything is an essential prime implicant. I have 5 essential prime implicant. I have kept them, so they are there, and that covers everything else. So I need not include any other prime implicant besides these 5 essential prime implicants. Let us quickly go through another example which explains one aspect. So let's look at example. I have a set of true minterms on mint, and I also have a set of don't cares. So 2, 12, 15. So the rule is that when I am making the first table, first tabular structure, I would include list of minterms, the on minterms, true minterms, as well as the don't cares. True minterms as well as the don't cares. So the don't cares are very much included in this list. And then I compare. Say, for example, 4 is a on minterm, 2 is a don't care minterm, both are there. Similarly, 6, 9, 10 are true minterms. Similarly, 12 is a don't care minterm, so don't care is also there. Now, I just follow the same procedure as before. I just keep on combining them. Okay. So the additional step introduced by this don't care is that I also include the don't care minterms in my combination strategy. And everything else is same before. So let's see what they combine. 2, 6 combines, 2, 10 combines, 4, 6 combines, 4, 12 combines. So these are the things that combine. So this is again the second level of that. So 2 1s with 3 1s. So 9, 11 combines, 9, 13, 10, 12, 13 combines. So these are the ones that combine. Similarly, 3 1s and 4 1s. I am including everything. I'm including 4, 6, 9, 10, 11, 13, 2, 12, 15. Everything I'm including and repeating the same procedure as before. 11, 15, 13, 12. We have 1 dash, 2 1s and 1 dash 3 1s. So these are the combinations that I have. These are the combinations I have. Hope I'm connected. Yes. Okay. So combine 2 1 1 dash and 3 1 1 dash. So I get 9 11 13 15 9 13 11 15. These are the ones that I combined. So you see these cannot be combined any further. So I stop here and I look at the prime implicants which are not combined with anybody else, and they would be my look at the implicants which don't combine, and finally I get the prime implicants which are this 2 6, 2 10, 4 6, 4 12, 9 11 13 15, 10 11 12 13. Now there is one more change because of this don't care. See, earlier I said for every min term there will be a column. So 4 6 9 10 11 13. Okay. But what I do is that I don't include the columns for the don't care minterms. I only include the true minterms columns. I don't include the don't care minterms column. Right. Why I don't do that? Because I don't need to cover them. Right. Since I don't need to cover them, so while finding out the prime implicants, I include the don't care terms. But for in the prime implicant chart, where I find the minimum prime implicant by covering all the minterms, there I don't include the don't cares. Okay, so while forming prime implicants, I include don't cares. While forming minimum prime implicants, I don't include don't cares. I include only the true minterms. Okay, so this is the one. So the only essential prime implicant here is 9. The only essential prime implicant here is 9. So which is covered by 9, 11, 13, and 15. So I should definitely, this should be there in the final expression, 9, 11, 13, 15, which corresponds to A and D. Okay, so that will be there. And since I have included 9, 11, 13, 15 because it is essential, I can as well drop 11 and 13 columns. I need not, they're already covered. I can drop it. I can form a reduced prime implicant chart. Okay, so now let us see another reduction that you can do. So one row will set to cover another row if so for example, let's see here 9, 11, 13, 15. What are the columns covered by it? So 9, 11, 13, 15 cover 9, X, X, X. So these 3 X are there. 3 X's are covered by prime implicant 9, 11, 13, 15. Let us look at 12, 13. 12, 13 covers only this X, the last column. So you see the X covered columns by 12, 13 is a subset of the covered columns of 9, 11, 13, 15. So this has only 1x, this has 3x, and this 1x is a subset of this 3x. So this is the set of columns covered by 12, 13 is a subset of the columns covered by 9, 11, 13, 15. So in this case, I would say that 9, 11, 13 dominates 12 and 13. This row dominates this row. Okay. The fifth row dominates the last. The fifth row dominates the last row. Okay. Similarly, you see 10, 11. 10, 11 dominates 2, 10. 10, 11 covers this and this. 2, 10 covers this. This is a subset of this. So 10, 11 covers 2, 10. Similarly, 4, 6 dominates 4, 12 as well as 2, 4, 6 dominates 4, 12 as well as 2, 6. Okay. So now the rule is that, see, I'm trying to reduce the rows. Okay. So the rule is, if I keep a dominating row, I can delete all the rows dominated by it. So if I keep 9, 11, 13, 15, I can delete 12 and 13. Similarly, I keep 10, 11, I can delete 2 and 10. If I keep 4, 6, I can delete 4, 12 and 2, 6. Okay. This, if I keep a dominating row, I can remove the dominated rows. So note one thing here, that 9, 11, 13, 15 was an essential prime implicant. So I have to keep it. There is no other way. I have to keep it. And if I have to keep it, this dominates 12. So I can remove the 12, 13 row. See, all that I'm trying to do is that this prime implicant chart, I am trying to make it small. I'm trying to make it small by dropping rows and dropping columns. One thing that I cannot drop, I have to be, it has to be there in the final expression, reduced expression of the essential prime implicants. I have them. But since I have to have them, the other columns covered by the essential prime implicants, they can be dropped. They are already covered. Similarly, if I keep a dominating row, I can drop all its dominating rows, right? So, so I can of course have an reduction. I can. So can you tell me what are the rows and columns that I can delete from this table? Anybody? What are the rows and columns I can remove from this table? Please tell me.
2, 6, 2, 10, 4, 12, and 12, 13.
Yes. And any column that I can remove from this? Yes. These are the columns and these are the rows I can reduce and form a smaller table. Let's quickly move on to another example. I'll explain. So this I'm quickly going through this first step of Quinn-McCluskey. So there are a lot of prime implicants here. But one thing you don't forget is that while I'm forming the prime implicant, I'm considering don't cares. Where I'm writing implicants, I'm not I do not need to cover that. Okay, this is another example. I repeat the same procedure. I group the main terms. Here there are only two main terms according to the number of ones they have their index, and I combine them to get these cubes. I'm just writing them 0, 1, 0, 2, 0, 8. I combine one index with two index. I get these cubes. These are the cubes. Again, I'm not speaking them out. So 2 with 3, I get these cubes. 2 with 3, I get these cubes. There is nothing left out, so there will be no prime implicants that I get from this table. And then now 3 with 4, these are the two cubes that I've got. Again, there is nothing left out, so there will be no prime implicants of size 5. Similarly, 4 with 5, 23, 31, and 30, 31. These are combined. Again, everything is combined. That is nothing left out. So these are the second level table with one dash. This and this and this. Now, the second level table also I group according to ones they have. These have 0 ones with one dash. These have 1 ones with one dash. And I combine them, I get 0, 1, 8, 9, 0, 1, 2, 3, 0, 2, 8, 10. Now here also is everything combined? No, 0, 8 is not combined. So this might form a prime implicant. This will form a prime implicant. Similarly, 1, 3, 1, 9, 1, 17, 2, 6, 2, 10, these are not combined. This also will form a prime implicant. Okay, so this is the second level. This is 1, 1, 1 dash with 2, 1, 1 dash. And this is okay. So see, finally I have 1, 1 dash for this. Okay. So actually 1, 1, 1 dash combined with 2, 1, 1 dash to form the ones with 2 dash. So I've just written it here for sake of space. So these are the ones. So I combine this with this, this with this, this with this, I get this. Right. Now I combine the ones with 2 dashes, so 0 ones and 1 ones, these two get combined. All right. So after this, again, you should go through these details. You should go through these details, but they are very simple. So these are the set of prime implicants I get, P1 to P10, 2, 6 with 3 variables, 7, 21, 3 variables, 20, 21, 3 variables. No, not 3 variables, 4 variables. So all these are prime implicants with 4 variables. This is a prime implicant with 3 variables, and this is a prime implicant with this with 3 variables. Okay, no, 2 variables. Okay, so these are the prime implicants I finally have by this first step of Quinn-McCluskey. And this is my prime implicant chart. This is my prime implicant chart. So basically, I have put a cross. I have listed all the true min terms along the columns. I have listed all the prime implicants that I have extracted. These are actually all the prime implicants that are there along the rows. And if a prime implicant covers a min term from this chart, I put a cross. Now what I'll do is that, see, my final goal, let me repeat my final goal, is that I have to find a subset of rows covers all the columns, put a cross in all the columns, no column is left empty. So pick a subset of row with the constant is it should cover all the columns, and the objective function is the combination of the prime implicates in the retained rows should have the minimum number of literals. So it's an optimization problem, constant optimization problem. Okay, it should cover all the columns, and the total number of literals in the reduced set of rows should be minimum among all subsets covering all columns. And this optimization problem is equivalent to what is called a set cover problem. Set cover problem is you have a set of objects and you have a set of subsets of the set of objects. Find the minimal set of subsets so that any element in the set belongs to at least one. At least this is the set cover problem. Computationally, this can be shown to an NP complete problem. Set covering is an NP complete problem. So this is equivalent to a set covering problem, and naturally it is an NP complete problem. But there are some reductions you can, but that does not deter you from solving this problem, because the size of the problem often will not be very large. You will deal with, say, how many, 5 variables, 10 variables, not more than that. So the size of this set will not be extremely large. Okay, but there are we have talked about set problem just by from the semantics of the problem. Some reductions we can do. One reduction is we know that the rows corresponding to essential prime implicants will always be there. They have to be written in the final set. They will be there. So the final solution, the set of minimal prime implicants, will always be a super of the essential prime implicants. Essential prime implicants will always be part of the solution. Okay, so we have to retain them, and if we retain them, the other columns covered by them can be dropped. Similarly, all the dominating rows can be retained and dominated rows can be dropped. Okay. Now, just we have dominating rows, we can also have dominating columns. We can also have dominating columns. Let me see if I have that. Let me state that then. What the hell? Yes. Yes. So the same rule will of domination will be there for the columns. Can you tell me? So that means if the crosses in a column is a subset of the crosses in another column, the second column is said to dominate the first column. So can anybody tell what are the a pair of dominating columns here? Can anybody tell a pair of dominating columns? Anybody?
Sir, column 9 dominates column 10.
Column 9 dominates column 10. Similarly, column 2 dominates column 3. Column 2 dominates column 3. Okay. So we can have a similar. But here, the rule is opposite. The rule is opposite to rows. That means if column 2 dominates column 3, I will keep column 3, I'll drop column 2. I'll keep column 3, I'll drop column 2. Okay, so it's the opposite. Earlier, if say for example here, say row P3, no, not row P3, row P9, no, not row. Is there any dominating row here? Let me check if there is a pair of row which are dominating. Can't find. Okay, in the row, what we did was the dominating row was retained, the dominated row was dropped. The columns is just the opposite. The dominated column is retained, the dominating column is dropped. So among 2 and 3, 2 will be dropped, 3 will be retained. Can anybody tell why this is the case? Can anybody tell why it is the case? Anybody tell? Because see, if I keep 3, then I need P10 to cover this. I'll need P10 to cover this. If I keep P10 to cover 3, it will also cover 2. It will also cover 2. Okay. So if I just keep column 3 and drop column 2, that is enough. Because 3 is a subset rows which cover column 2. So if somebody who covers 3 will definitely also cover 2. Somebody who covers 3 will cover 2. So I can keep 3, drop 2. Okay, so let me repeat the process. So there are 3 reductions I talked about. One is you have to keep the essential prime implicants. And if you keep the essential prime implicants, other columns covered by the essential prime implicants can be dropped. If you have dominating rows, you keep the dominating row, drop the dominated rows. If you have dominating columns, keep the dominated columns, drop the dominating columns. Okay, so these reductions I can do. So let's see what happens here. First, let me identify the essential columns. Column with only x. So 0 is a column with only 1x. Okay. So if 0 is the only column with only 1x and 25 is a column with only 1x. So I have to cover 0. So only P10 covers 0. So P10 is C bar is an essential prime implicant. Since P10 is an essential prime implicant, it has to be there in the final minimal. And since it is anyway there in the final minimal expression, I can drop other row columns covered by P11. I drop 1, 2, 3, 8, 9, 10, 11. I can. Okay. So see, I drop them, I get a reduced chart. You get a reduced chart. Okay. Okay. So this is the reduced chart I have. Now you see in this reduced chart, 6 is an essential column. So P1 is an essential prime implicant. So P1 should always be there. P1 is A bar, B bar, D, E bar, P1 is there. And if P1 is there, I can drop this column because I've already covered. In fact, since P1 will always be there, I can drop this row also. So that's what I forgot to mention. See here, you can drop P10. You can drop the P10 row because I have already included. So I drop P10, P10 is not there. P1 I drop, P1 I drop. So this is my reduced thing. So I have P2 to P9 and only the columns that are not covered by P1 and P10. See, I find 25 is another essential. Only P9 covers it. So P9 will be 25 will be gone. P9 also covers 17. So 17 will be gone. So I get an even more reduced table. Now you see among P2 and P3, P3 dominates P2. So I will keep P3, I'll remove P2. I'll keep P3, I'll remove P2. This is even more reduced. Okay. All right. So now let us look at the columns. So you see 20 no, not 20, 20 minutes. Here I have dropped. The moment I drop P3, moment I drop P3, 2021 both gets dropped. 2021 both gets dropped and P3 gets dropped. This is my reduced table. So you see it's much reduced. I have only 4 columns and 5 rows. Now you see P6 dominates P4. I will keep P6, I'll drop P4. P6 dominates P4, I'll drop P4. Now you see P5 dominates, P7 dominates P5. I'll keep P7, I'll remove P4, P5. This is my even reduced table. Now you see 31 dominates 23. Column 31 dominates column 20. So what I will do is that I will keep 23, I'll remove 31. I'll keep 23, I'll remove 31. So I keep 23, I remove 31. Right. So this is my even more reduced. Now you see that P6 dominates P8. P6 dominates P8. So I'll keep P6, I'll remove P8. I'll keep P6, I'll remove P8. Okay. Now again here P7 is an essential, so I have to keep P7. Similarly, P6 is also essential, so I have to keep P6. So these are my final set of prime implicants, minimal prime implicants. Okay, so see, let me take another thing that see there is another thing you can do. All right. So now one question you will ask. Let me see if I can explain with this. Okay, so these are all essential cubes. So now let us come to this example again. So this is kind of reduction. See, one thing you might have already noticed, I've applied some reduction step. If I change the sequence of this reduction step, I might get something else. So I'm illustrating that. Now this is an prime implicant. Then I remove this as an essential prime implicant. I get this. I get this as an essential prime implicant. Then I remove that. Similarly, I get this. This is a dominating. P6 dominates P7. So I get this. So there are, and P8 is an essential cube. So there are distinct solutions you can get by this minimization process, depending on what reduction you do first. There can be solutions you can get. And all these are minimal. Both of these are minimal. Both have the same cost. Cost is number of literals, total number of literals. Okay, so let me quickly explain one more thing. All right, so write something. Let me see if I can, yeah. What? Anyway, let me speak out. All right, so let me just tell you what I want to say. So you see, after applying these reductions, you might come with a reduced prime implicant chart where no further reduction is possible. You might come. So this final prime implicant chart is called an cyclic core. It's called the cyclic core of the original prime implicant chart. Okay, so see other things, the cyclic cores are, if you remember the Carnot map, you have seen that there are some true main terms which are not covered by others. So there is a cyclic kind of covering that you can have. So this actually, if you plot in the Carnot map, they will represent those cubes. So the final prime implicant chart after all this reduction, which cannot be reduced further by any of these four essential prime implicant, dominating row, dominating column, any of this is called a cyclic core. Now, all the essential prime implicants I have included. So from this final cyclic core, I have to add something to that because these are still uncovered by the essential prime implicants, so that you get the minimal set of prime implicants. This is an optimization problem. In fact, this is an instance of an optimization problem called the unit cover problem. This optimization problem has to be solved by standard search methods. You have to find out, so it's a constant search. You have to find out you have a reduced set of parameters. You have to try out all possible, not try out all possible. You have to try out exhaustively. You would have to try out all possible subsets, then check if they cover all the remaining crosses in the cyclic core. If they cover, you have to check their cost. And among all possible subsets of this reduced set of prime implicants, after removing the essential ones, which cover all the crosses in the cyclic core and which have the minimal cost, you have to search them out. So in general, this search, you can do an exhaustive search, another thing. In general, you cannot have a polynomial time algorithm because this is equivalent to the set cover problem, which is known to be an NP complete problem. But there is one property you can exploit. The property that you can exploit is if you have two prime implicants where one is subset of the other, or it has less number of literals, then the cost is more for the second one. Okay, cost is more for the second one. Okay, so this is typically used in a search algorithm called the branch and bound algorithm. It's a branch and bound algorithm. Those who have done the algorithm course might have already know about it. It's the branch and bound algorithm. So you construct a tree, not a balanced tree, an unbalanced tree, where the leaves represent all possible subsets of the remaining prime implicants. Okay, and then when you are trying to find the minimal, so you have, if it doesn't cover, you drop it, otherwise you include it in the tree. You can actually compare, without backtracking, you can compare one node in this tree with the leaf nodes. And if you already have a bound on the cost, if the cost exceeds this bound, you don't explore, you don't build that. This is the typical branch and bound algorithm. Maybe in the next class we'll discuss, or okay, I can give you the reference also. So if you have a cyclic core, which is not reducible further, you have to use the branch and bound algorithm to find out the solution. There are some heuristics also to solve this. There is one heuristic is called the independent set heuristic. Independent set heuristic means you take two columns whose crosses do not intersect. They do not have cross in the same position. Then they are called to be independent columns. So you rearrange the prime implicant chart so that the independent columns are all in the beginning. You put those columns first, independent columns. And then you do an search over only the independent column. So this is an heuristic. There is another heuristic called which is slightly advanced of this, is called an espresso heuristics, which uses, see, this is an NP complete problem. So now normally you cannot have a polynomial, but many of these heuristics which take into account the problem information, they can help you search faster on the cyclic core. But cyclic core, after that, no further reduction is possible. So either you have to run branch and bound, which for large sets can take time, or you have to use some heuristics. In practice, heuristics are more commonly used than the exhaustive search methods. Okay, so I think that's it. That's where we stop this Cohen-McCluskey. We are at the end. So in summary, we have two steps. First step is just keep on combining and dropping, forming dashes or don't care. Then you get the set of all prime implicants. Then you form the prime implicant chart, whose rows are these prime implicants extracted and the columns are the true main terms, not the don't cares. In first step, you include the don't cares, and then you do a certain set of reductions. First, you identify the essential prime implicants, drop their rows and columns covered by them. Then you find dominating rows, keep the dominating rows. Find dominating columns, keep the dominated columns. This reduction with the cyclic core, which is a small prime implicant chart. For there, multiple solutions are possible. In fact, for all of these, multiple solutions are possible. Each of these might be equal cost, so any of them is okay. Then from the cyclic core, you run a search algorithm, usually the branch and bound search algorithm, to find out the lowest cost prime implicant. Basically, you add some prime implicants from the cyclic core so that it covers all the columns in the cyclic core and is of minimum cost. Essential prime implicants are there, you cannot touch them. You just add the minimal ones to them. There is one more kind of a trivial method of solving this. If you have the cyclic core, let's say this is a cyclic core. Let's take this. Let me take another example. Maybe not a cyclic core, but still I'll use it to explain another method called the Petrik's method. Okay, so what the Petrik's method does is that it let me show you a prime implicant chart, small prime implicant chart. Let me go to a reduced one. Yeah, this is a sufficiently reduced one. See, here you see, to cover all the columns, you need P6. You need P6 or P7. P6 or P7. Sorry, you need P6. So you see 28 is covered by P6, 30 is covered by, so 28 covered by P6, 30 is covered by P6 as well as P8. So you need P6 or P8 to cover 30. You need only P6 to cover 28. You need only P7. So I can write this as an expression. I can write this as P7 and P6 and P6 or P8 and P7 or P8. Okay, so it's P6 first column and P7. It's P7 for the first column and P6 for the second column and P6 or P8 for the third column and P7 or P8 for the fourth column. This is a logical expression. P6 times P7 times P6 times P6 plus P8 plus times P7 plus P8. So this is a product of sum from. If you convert it to sum of product, maybe you will get, say, let's say P6 P7 plus P7 P8. You convert it into sum of product from. So any of these P6 P7 plus P7 P8. So P6 P7 is a solution for the minimum prime implicant. Similarly, P7 P8 is a solution for the each of these alternate solutions. Okay, you might pick up the minimum amount. Convert the product of sum from this prime implicant chart. And how do you form the product of sum? You look at each column and connect up the crosses with a OR, and each column you connect them by a AND. Convert it, you get a product sum, convert it to sum of product. Each term in the sum of product is an minimal prime implicant. And you pick up the minimum. If you look at, you talk about cost in terms of number of literals, you pick up the minimum amount. So this is the matrix method. So I kind of summarize all the steps we have done. So in this, statement. Yeah, this is the entire summary of the statement. Okay. All right. So I think this is all about Quinn-McCluskey. You have to practice some problems. We will give you some assignment problems to practice on these as well as the. But we are at the end of the Quinn-McCluskey. Thank you.
Hello.
Yeah, please tell.